This is the 34th video in a series that I'm making to support a course in elementary number theory. And I'm pretty sure this is the next to last video. So I already wrapped up my course with the previous video, but I thought I would add 2 videos to this playlist so that we could prove the Thame-Rogers-Ramanujan identity. Now, some of you guys might know that I started a series a long time ago with the aim of proving this identity, but I never got around to finishing it. Well, it turns out that I think this playlist is a better place to finish it because I've covered all of the necessary information, and I think everything is done a little bit more nicely. Before we get into the major goal of this video, I want to recall a few things and look at some examples. So let's recall a partition of n named lambda is a k-tuple. This partition is said to have k parts if it satisfies 2 conditions. So it's non-increasing. So in other words, lambda 1 is bigger than or equal to lambda 2, which is bigger than or equal to lambda 3, all the way down to lambda k. And I should really include here that lambda k is bigger than or equal to 1. So these portions are made up of natural numbers. And then furthermore, we have lambda 1 plus lambda 2 all the way up to lambda k is equal to n. Now let's recall that generating functions are an important tool for studying partitions and coming up with partition identities, as we've seen in previous videos. And so if we set P of n equal to the number of unrestricted partitions of n, that's sometimes called the partition function, then the generating function for P of n, sometimes called P of q, so that's going to be the sum as n goes from 0 to infinity of P of n q to the n, where we take P of 0 to be 1, that's equal to this infinite product of things that look like sums of geometric series. So the product is m goes from 1 up to infinity of 1 over 1 minus q to the m. And we had some notation in previous videos using this thing called the Pockhammer symbol that allowed us to write this as this q in parentheses with an infinity. Now, before we get into the main goal of the video, I want to recall why this generating function works. So if we take this sum as n goes from 0 to infinity of P of n q to the n and write it out as the product, so we've got 1 over 1 minus q, 1 over 1 minus q squared, 1 over 1 minus q cubed, and so on and so forth forever, then each of these portions of our rational function or our infinite product give us certain things related to the partitions. So this 1 over 1 minus q controls the parts of each partition that are equal to 1. This 1 over 1 minus q squared term controls parts of the partition that are equal to 2. And what I mean by parts, that's these individual things that are making up the partition. And then 1 over 1 minus q cubed, those are parts that are equal to 3. Furthermore, if we expand each of these as geometric series, which you should really think about these as being expanded as geometric series, that's the more proper way to view this infinite product, we can see a little bit more of what's going on. So for instance, this 1 over 1 minus q, we can think of it as expanding to 1 plus q to the first, q to the 1 plus 1, q to the 1 plus 1 plus 1. And each of these controls how many parts of the partition are equal to 1. So this number 1 here corresponds to not using 1 at all in the partition. This corresponds to a single part which is equal to 1. Here we have 2 parts equal to 1, 3 parts equal to 1. And then we've got similar rules for 2, 3, 4, 5, 6, and so on and so forth. So this q squared corresponds to 1 portion of the partition equal to 2. This q to the 2 plus 2 is 2 parts equal to 2. And then, well, that continues on. So let's look at some examples real quick, just to recall maybe how these things are built. Let's find the generating function for partitions where all of the parts are congruent to 1 or 4 mod 5. Let's first recall that being congruent to 1 or 4 mod 5 means that we are of the form 5m plus 1 or 5m plus 4, where m is bigger than or equal to 0. But m could be anything bigger than or equal to 0. So keeping in mind that these types of rational functions control what parts we're using, we can write down a generating function pretty easily, and it would look like this. 1 over 1 minus q to the 1 power. That would be using a part that is equal to 1. 1 over 1 minus q to the 4th power. That would be parts equal to 4. And then the next number that is 1 mod 5 is 6. So that's what we would have next. 1 over 1 minus q to the 6. Those are using parts that are 6. The next number would be 9 because that is 4 mod 5. So 1 over 1 minus q to the 9. And that's going to end up being an infinite product because there are infinitely many numbers that are congruent to 1 or 4 mod 5. We could end up writing this as the product as m goes from 0 up to infinity of 1 over 1 minus q to the 5m plus 1 times 1 minus q to the 5m plus 4. And there's a simplified way to write that down using our pock hammer symbol, which I'll have come on the screen right now. Now we could do something else. Let's say we wanted to find the generating function for partitions where the parts are used at most twice. Then, instead of thinking about the rational function, we want to think about its expanded form. So only using them twice means that we cannot include anything past this point, because this q to the 1 plus 1 plus 1 corresponds to using the number 1 3 times. And then furthermore, everything past this point corresponds to using the number 2 3 or more times, and then so on and so forth like this. So that means instead of an infinite product of geometric series, we have an infinite product of just polynomials. So here we'll have 1 plus q squared. I'll write it as q squared instead of q to the 1 plus 1. So that corresponds to using 1, 0, 1, or 2 times. And then we'll have 1 plus q squared plus q to the 4th. That corresponds to using 2, 0, 1, or 2 times. 1 plus q cubed plus q to the 6th, and then so on and so forth. Okay, well, we could write that with a product notation as the product as m goes from 0 up to infinity of, or maybe we should go from 1 up to infinity in this case. I think it'll be written down a little bit nicer. Then we'll have 1 plus q to the m plus q to the 2m. So this portion would be like using a part which is equal to m 0 times, 1 time, or 2 times. Now there's a nice identity that I assigned to my class which allows us to write this object in another form, which represents partitions where the parts are congruent to 1 or 2 mod 3. That's a pretty famous result. I'll let you guys try that on your own if you're interested. Okay, so now that we've got this kind of review under control, let's see what our main goal for the video is. So our major goal for this video will be to find a generating function for a certain type of restricted partition. But that restricted partition is not quite as simple as the ones that we just looked at. In particular, we want to find the generating function for partitions of n where adjacent parts differ by at least 2. So just as an example, although you could easily write down a lot of other examples, and I urge you to get a feel for what these look like. If n equals 9, we have 5 total partitions that satisfy this rule. So the first one will be 9. Well, that has a single part, but that means there's no adjacent part to have this difference condition. So we're good to go there. So the next one is 8 plus 1. 8 and 1 clearly differ by at least 2. 7 plus 2, 6 plus 3 are the other ones that have length 2. So notice the next one kind of in this vein would be 5 plus 4, but the difference between 5 and 4 is not at least 2. So we go down to a partition of length 3. And that would be 5 plus 3 plus 1. So notice that sums to 9, and there's a difference of 2 between each one. And this represents all such partitions that satisfy this rule. Okay, so now that we've got an idea of the goal, I need to define a couple of functions which will be helpful as we work towards this goal. So the 2 functions that we'll need for our goal are defined like this. So I've called them f of mn and f hat of mn. So f of mn is the number of partitions of n into m parts that differ by at least 2. So maybe if you're having trouble figuring out what this means, look back at our example for n equals 9 and notice that m could be equal to 1, 2, or 3 in that case. If m was bigger than 3, then we would get 0 for this. Okay, and then f hat of mn has the same condition as this one up here. In other words, it's partitions of n into m parts that differ by at least 2, but in this case, none of the parts are equal to 1. So that means the smallest possible part here is equal to 2. And then since we're looking for generating functions, I will define two variable generating functions based off of f and f hat. So I've called them capital F and capital F hat. So capital F of xq is the sum over m and n, so it's a double sum. F evaluated at mn, x to the m, q to the n. So our x variable is counting the number of parts, and our n variable is counting the partition that we're looking at. And then f hat of xq is defined similarly, just with f hat here. So remember, our goal is to find the generating functions for parts like this. And so that would be related to this pink box here. So we'll start with the following proposition. It has 2 parts, and it's some sort of recursion between these 2 functions. So we've got f of mn is equal to f hat mn plus f hat m minus 1 n minus m. And then the second one is f hat mn is equal to f mn n minus m. Okay, so let's see how this proof goes. And I think maybe the best approach to this proof is like kind of visual. So let's start up here and say that this box contains all partitions of n with m parts that differ by at least 2. So by the definition of our function over here, we know exactly how many elements are in this box. So there are fmn elements in this box by the definition of fmn. And then looking up at our goal, we see that we want to separate this number fmn into 2 pieces. So that means we should probably take each of the elements in this box and naturally partition them into 2, maybe like sub boxes, we could call it. So I'll bring one down here to the left and one down here to the right. And let's see, how should we do this? Well, obviously we should do this in a way so that one of them contains f hat mn elements and the other one contains that many elements. Well, it turns out it's easy to do this one. So notice that these will be partitions of n with m parts differing by bigger than or equal to 2, and then here not equal to 1. That's like the definition of this f hat mn. So that means there are f hat mn elements in this box. Okay, so we can't just write this next one down, but what we can do is talk about what is not in this orange box, and that's exactly what we'll do. So let's go over here, and we'll describe the complement of this orange box. So this will be partitions of n into m parts that differ by bigger than or equal to 2, and they include the number 1. So that means each partition in this box has the number 1 as the first part. Notice it can only be the first part if it satisfies this rule. So I would suggest a nice doable exercise would be to pick a value of n and m and fill all of these boxes in. Okay, so now what can we do? We want to somehow translate these types of partitions into partitions that are being counted by this function. And that's not too hard. So what we'll do is subtract 1 from each part. Okay, So that means that we're eliminating the last part, and then we are decreasing n by m. Okay, so let's see what effect that will have. So that will assign each partition up here to a partition of n minus m. Well, why did we have to subtract m? Here, I just said we subtract 1. We are subtracting 1 from each part, and there are m total parts. So that means altogether we're subtracting m. And then furthermore, because we're subtracting from each part, they still differ by at least 2. But now since 1 was definitely one of the parts up here, and we subtracted 1 from each part, that means we've decreased the number of parts by 1. So this is partitions of n minus m into m minus 1 parts. And then since we subtracted 1 from every part, this rule is still satisfied. So in other words, all of these differ by at least 2. The parts differ by at least 2. So I think it goes without saying, or maybe it's a pretty easy thing to see, that this sets up a one-to-one relationship between the elements in each of these boxes. So now all we have to do is count how many guys are in this box. But that's not too hard because we've got a function that counts that exactly. And that is f n minus m, m minus 1. In other words, partitions of n minus m into m minus 1 parts. But notice we almost have everything we need to build this equation. We just need a hat over this. So how can we argue that there's a hat over this? In other words, that none of these parts include 1. Well, that's not actually that hard because here, every partition includes the number 1, which means the second smallest part is bigger than or equal to 3. So when we subtract 1 from each part, the smallest part down here will be bigger than or equal to 2, so it will not include 1. So by those rules I've just said, that means we can put a hat over this. But now what we've done is created some sort of disjoint union of our set at the top into these two sets here, which have f hat mn and f hat n minus m, m minus 1 elements, whereas our original set had f of mn elements. So that builds this first equation. Okay, so let's maybe get rid of this and then we will build the second equation. We just got done proving this first equation. Now we're ready to prove this second equation. So let's see how we can do this. We'll do a similar strategy where I make a box where I put all of the partitions of a certain type. So I want to count up the number of partitions that this function represents first. So these will be partitions of n minus m with m parts. And maybe this goes without saying because this is the whole world that we're living in this video, but these parts differ by at least 2. So how many elements are in this box? Well, there are exactly fm n minus m elements in this box. Okay, what will we do here? Well, we're going to do a similar transformation to what we did on the last board. So I'm going to set up this one-to-one correspondence, which is generated by adding 1 to each part of every partition in this box. Okay, so let's see what effect that will have. So that's going to give us partitions of n instead of n minus m, because we've added 1 to each of the m parts. So in the congregate, we have added m. And then, but we have not changed the number of parts. So this is still with m parts. They still differ by at least 2. And furthermore, since 1 was the smallest possible part here, the smallest possible part down here is 1 plus 1. So that means these don't include the number 1. Okay, but now we can easily count up the number of partitions in this box, and it's exactly what we want it to be. It's f hat mn. Now we're going to take this result and write a generating function version of it. In other words, a version of it that involves these capital F and f hat functions. We just got done proving a nice recursion for these functions little f and little f hat. And now we want to look at a generating function version of those recursions. So we've got this first one, capital F of xq is equal to capital F hat of xq plus xq capital F hat of xq. And then the second one, f hat xq is equal to f xq. So let's start with this first one. And as we'll see, these follow pretty quickly from the recursions that we just got done proving. So we'll start with the left-hand side of this. So we have f of xq is equal to our sum over mn of f of mn x to the m q to the n. Nice. Now I'll apply our first recursion to this little f mn. So that's going to give us this sum as m and n go between 0 and infinity, although I'm leaving that off, of f hat mn plus f hat m minus 1 n minus m. Then we've got x to the m, q to the n, like that. Now we're going to split this into two parts. So that's going to give us this sum as m and n go between 0 and infinity, f hat mn xm q to the n. So notice that is already our generating function capital F hat. And then we've got the rest of this. So that's going to be plus our sum over m and n of f hat m minus 1 n minus m x to the m q to the n. So like I said, this guy right here looks exactly like our f hat generating function already. So I'll just rewrite this as f hat xq, and then we can get to work on this other bit, which will require a little bit of reindexing. So let's see how we might want to reindex this. Well, I think probably our best bet will to send m to m plus 1. So in other words, we're going to replace all of the m's with m plus 1s. And then what should we do with the n's? Well, we're going to send all of the n's to n plus m. Now, you might be a little bit worried about what's happening kind of at the lower end here because we have to change the starting point. But I'll let you guys think about why that is not a problem. We're essentially just counting and leaving out a bunch of zeros. So how does that allow us to rewrite this guy? That allows us to rewrite this guy as the sum over mn of f hat mn, and then we'll have x to the m plus 1, q to the m plus 1 plus n. Now what we'll do is factor some stuff out of this and rewrite it a little bit. So this is going to be x times q times our sum over mn of f hat mn. And then what's left over after we factor that bit out? So we will have x times q all to the m power. I've put those together just because that's what's being clued into us over there. And then we will have q to the n power. But let's notice that if we were to rewrite this using our f hat generating function, it would be exactly this term right here. So that means we have proven this first identity. And then maybe this second one is a nice one that could be left as a little bit of a homework exercise. It follows pretty similarly. Okay, so now we've got everything in place to achieve our goal. Now we're ready to prove our goal, and that is the generating function for partitions with this restriction. So we've got f of 1q is equal to the sum as n goes from 0 to infinity of q to the n squared, and then this pockhammer symbol qn. So recall that's a product of n objects in the denominator. You might say, well, what's this 1 here? Well, the 1 allows us to count the number of partitions without worrying about this restriction on the number of parts. I'll let you guys think about that a little bit. Okay, so let's get to the proof. So from the previous proposition, we can put those two portions of the proposition together into this single equation. F of xq is equal to f of xqq plus xq times f of xq squared q. So let's recall that the part that we proved had something with hats over here on the right-hand side, but the part that I left as homework would allow you to translate those into just the standard f's without the hats. Okay, so next we're going to assume that we have the following expansion. So f of xq is equal to the sum as n goes from 0 up to infinity of an times x to the n. So those an's are going to all depend on q. And I want to point out that it's not too hard to see that a0 should be equal to 1. Well, that would be like the number of partitions with 0 parts, but we take things like that to be equal to 1 generally. Okay, so now we'll plug this expansion into our recursion or our difference equation up here, and that will give us the sum as n goes from 0 up to infinity of an x to the n equals the sum as n goes from 0 to infinity of an times q to the n x to the n plus x times q times the sum as n goes from 0 to infinity of an. And then let's see what we've got here. We've got q to the 2n and then x to the n. So we've got something like that. So next, I'm going to take this x times q and bring it in, and we can bring it in by adding 1 to each of these exponents. So we have q to the n plus 1 and x to the n plus 1. Next up, I will re-index this sum so that my x has an nth power. So I can do that by sending n to n minus 1. So that means n plus 1 will be, well, n minus 1 plus 1, which is just n. Okay, so let's see what effect that has. So that's going to give us the sum of a sub n minus 1 q to the 2n minus 1. That's the effect if we replace n with n minus 1, and then x to the n. But now this is just going to be the sum as n goes from 1 to infinity because of our changed index. Next up, we can see that the only two constant terms in x are equal to 1, and they occur in this sum right here and this sum right here. So we can subtract a0 from both sides, and that will change this from a starting point of 0 to a starting point of 1, and likewise over there. So we're running out of room, so what I'll do on the next board is rewrite this thing that I've underlined in yellow, and I'll probably push these two sums together. So after pushing the sums together on the last board, we have the following. So the sum of an x to the n is the sum of an qn, an minus 1 q to the 2n minus 1 x to the n. So now we can equate coefficients of x to the n on both sides of the equation, and we've got this nice recursion for a sub n. So let's see what we've got. We've got a sub n minus a sub n q to the n is equal to an minus 1 q to the 2n minus 1 after moving this thing over here. Next, we can factor an a sub n out of the left-hand side. That'll leave us with a sub n 1 minus q to the n is equal to an minus 1 q to the 2n minus 1. That tells us that an is equal to q to the 2n minus 1 over 1 minus q to the n times an minus 1. And now we can just iterate this recursion. So we can replace an minus 1 with q to the 2n minus 3 over 1 minus q to the n minus 1, and then we'll have a sub n minus 2. And then likewise, we can replace an minus 2 with another term times an minus 3. And we can do that all the way down until we get a0, which is 1. And then we'll have q to the 1 over 1 minus q, like that. But now let's see. We can multiply that together. Notice if we multiply the denominator together, we get exactly that q Pockhammer symbol, which is up here. Then if we multiply that numerator together, I claim that we get q to the n squared. You might say, well, why is that? Well, by exponent rules, what we have up here in the numerator is q to the 2n minus 1 plus 2n minus 3 plus all the way down to plus 3 plus 1. But it's well known that if you add all of these odd numbers like this, you get n squared. But now let's notice that we're actually done. If we take this expression for a sub n and put it back up here, then we have actually derived something a little bit stronger than this. And that is that fxq is equal to our sum of qn squared over qn x to the n. But then replacing x with 1 gives us this, which is the generating function for partitions of n where all of the adjacent parts differ by at least 2. And that's a good place to stop.